Okay, so moving on here. So I started to describe this a little bit in the last um, video, but I want to focus in a little bit more on this relationship between line spectra and atomic structure. So one of the things that was learned by scientists when they were trying to kind of pull apart the structure of atoms and how electrons are actually organized in there is that there are levels within the structure of an atom, and that electrons can only exist at certain energies within that structure. And this is called quantization. And one way to think about that, right, and this is not what it really looks like, but it's a way to kind of help understand what's going on, is you can kind of envision the nucleus of the atom as maybe the floor, and then the levels within the structure of the atom as kind of rungs of a ladder. And electrons can kind of sit on those rungs, but they can't exist in between those rungs. They can only approach so close to the nucleus. And what we see in atomic spectra or a line structure for every atom is the representation of where those levels are and their differences in energy. So if we think about a fairly straightforward atom like a hydrogen atom, there's a nucleus with one proton in it, there's one electron. That electron generally is going to live on the lowest level. That's going to be the lowest energy well for the interaction between the electron and the positive charge of the nucleus. Now, if we disturb that electron, right, we run a current through it, we burn our sample containing those atoms, we're going to provide energy, and that energy can move the electron up to one of those higher rungs on the ladder or a higher energy level within an electron. So energy goes in, and what may happen is the electron, say it moves up to the third level. And I know my levels are not at the same position, but the electron's in a different energetic state now. Now, after it jumps up, there's an attraction. There's still an attraction between the electron and the nucleus. The electron can now fall back down. So let's just say it falls back down to where it was, to the first energy level. The distance between those two energy levels, that'll be an amount of kinetic energy that is going to be released from the atom. So there's a change in potential energy when the electron is moving back and forth. Those changes in potential energy could be converted into kinetic energy. That kinetic energy is light that comes out. So when the electron falls, we get light. Right? H nu, the frequency of that light relates to its energy, right, and to its color, right, also its wavelength. So there may be a different color associated with the movement of electrons between these different levels within the structure of an atom. When we look at different atoms, we see different combinations of colors. Lines are at different positions because there's different energy there. And this observation of these line structures was one of the ways that scientists first started to piece together what is happening inside of atoms and start to make sense of that, and then develop it in a way that gives us kind of a broader understanding of what's going on in atoms and how we can start to organize atoms into something like the periodic table. Now, I just want to highlight a couple other important aspects here, and then we'll jump into quantum numbers, which is kind of a technique to understand the organization within the periodic table. I would highly recommend that you read through the chapter 7 in your textbook. It'll give quite a bit broader explanation of kind of the historical development of these theories, right, and what we now understand about the structure of atoms. It turns out that waves are pretty important in understanding how electrons work inside atoms as well. So initially, this was an idea that applied to light. Light always appeared to look like a wave. Einstein was actually the person credited with kind of deciphering some experiments with the idea that, well, maybe light can also act as a particle. So the effect was called the photoelectric effect, and Einstein was one of the first people to kind of come along and offer an explanation that, well, maybe light has this kind of dual personality, that sometimes it behaves like a wave, sometimes it behaves like a particle, right? And that's part of the nature of light. Turns out that's the nature of all moving objects, that every object that is moving has an associated wavelength. And really depending on the size of the object compared to the size of that wavelength, sometimes we have to consider wave-like properties, sometimes we don't. We can just consider particle-like properties. For electrons are vanishingly small, and they generally are moving pretty fast. We do have to think about them as waves. So there's an equation here that actually relates wavelength to Planck's constant, mass, and this is a regular v here, so it's velocity. So you can calculate a wavelength for any moving object if you know its mass and its speed. Right? For everyday objects, like say a baseball or a moving car, even a walking person, the wavelength is vanishingly small compared to the size of the person. So we don't have to worry about cars starting to behave like waves as they're driving down the highway. But for electrons, we do need to think of them as waves, and there are some consequences to this that help us kind of lead into our understanding of the structure of the electron configuration inside atoms, and help us understand how bonds start to form, that sort of thing. We'll see that as we continue on. The other kind of really important thing to recognize, and this, at least in my understanding, is a function of wave properties as well. There's this idea called the uncertainty principle, and I have it just stated here the way it's actually phrased. It is inherently impossible for us to know simultaneously both the exact momentum of the electron and its exact location in space. So basically, if you know where the electron is, you can't know very much about its momentum. If you know how much momentum it has, you can't really know where it is. There are similar corollary relationships, for instance, between time and energy. Over really short time scales, you really can't know anything about the energy of a particular particle. Right? And if you know a lot about the energy, you kind of lose track of how that particle is existing with respect to time. As a result of this, right, we need to think of electrons more in terms of areas as opposed to where exactly is the electron. Because if we have a little bit of an idea of what the energy of the electron is, now it exists kind of over a spread of space. This is what we'll see in a little bit as an orbital. So we have to take what we know about how electrons actually exist into account to try to figure out what we can then derive in terms of bonding, interaction of atoms, that sort of thing. So keep that in mind. Now, to finish off this video, right, the uncertainty principle, this is often termed Heisenberg's uncertainty principle because Werner Heisenberg was the original person who came up with this idea, right, fitting in with a lot of other developments that were happening in terms of electronic structure and understanding what's going on in an atom. So there's a joke that goes along with this that says, Heisenberg was driving in his car and he gets pulled over by a police officer. And the police officer says, "Excuse me, sir, do you know how fast you are going?" And Heisenberg says, "No, but I know exactly where I am," right? So he doesn't know how fast he's going, he doesn't know his momentum, but that means he knows where he is. And the police officer says, "Well, sir, you were going 75 miles an hour." And Heisenberg then says, "Oh, great, now I'm lost," because if he knows his speed and the momentum of his car, now he can't know where it is in space. So yeah, I don't know if that's a great joke or not, but it kind of highlights what's going on in the principle there in a humorous way. The other thing maybe to mention here at the end of the video, if you've ever watched Breaking Bad, so I think like most chemistry teachers, I really associated with the characters in Breaking Bad and really enjoyed the show. The main character, Walter White, takes on the alias Heisenberg in the show. Now, I've never seen any explanation of this from like the creators of the show, but it always struck me that perhaps one of the reasons he took on the name Heisenberg was because of the two different aspects of his personality. He's got the mild-mannered chemistry teacher, and then he's got this ruthless drug kingpin. And he kind of moves back and forth between those personalities through the course of the show. And almost like the uncertainty principle, right? The more he kind of settles into one of those personalities, the more he loses his connection to the other. So when he gets really involved in the drug aspect of his personality, his relationships with his family start to suffer because he's lost that person he used to be, right? And then when he tries to get out and move back into his good natured personality, he loses that kind of ruthlessness that was part of the drug thing. So I think there's, you know, a metaphor going on there about the uncertainty principle within kind of the other artistic directions of the show. Okay, we'll call quits there for this video, and we'll pick up with quantum numbers in the next video.